CSIS 2430 is filmed before a live studio audience.
Well, you're probably all wondering why I've gathered you here today. And it's to finally answer the question, what's the purpose of this propositional logic stuff? We've talked about a few purposes, but here's one that's very, very directly related to computer science and computer architecture, and it's all thanks to Mr. George Boole. We're going to talk about him in a little bit. But let's just take a little reminder of what we looked at just the other day. We looked at this idea of a circuit. I believe these are the exact circuits we looked at. We start off with the one on the top, and we're able to see that its output would be P or not R or not Q and R, right? And then I showed, in the other video, I don't believe I actually explained how. We just kind of talked about it, but it can be reduced from this top circuit to this bottom circuit. And I'm going to prove to you by showing you in this little circuit simulator that I have that those are the exact same circuits. So let's take a look at that real quick. All right, what we're looking at here is both of those circuits in an actual interactive tool here, where if I click on one of the letters here, it applies voltage and it gives us the output of what the circuit will be. So if I apply something to P here, we see that the output is 1. And if I make P not applying voltage, it's still 1 because we have these inverters here. We have an inverter here and an inverter here. So R being 0 going directly into the inverter comes out as, well, being true, being false. So R being false going through the inverter becomes true. Therefore, we have a true going into our OR gate here. And same thing with the Q. It goes in. Now, again, we notice here that we have 0 or false going into the AND gate. So the output of the AND gate is false. But when it gets through the inverter, it becomes true. And if you recall, we mentioned this the other day, that it's more, when you're talking about circuits, it's not true or false, it's high voltage and low voltage, right? So there's low voltage being applied on all three of them at the moment. Well, no matter what I put up here, if I do the same thing down here, I get the same results. And to streamline this so that we don't have to keep clicking on both of these circuits, what I've done here is created another circuit, which is both of these circuits just using the same power source. If we flip back to the other one, you can clearly see that's the top circuit. There's the bottom circuit, right? All I've done is just made one input of the P, R, and Q instead of two separate P, R, and Qs. So now we can see what happens to each circuit when I do something on P or R or Q. And no matter what I do, if you just watch these two circles here, the one here and the one here, you watch, those will always be the same no matter what I do over here. So I'm clicking on P, then R, then Q, and R, and then P, and nothing, no matter what I do, it looks like the output's always going to be a 1 in this particular case, no matter what I do. Okay, so that's pretty straightforward, but we can see that this second circuit is a reduction of the first one. So let's look at a little bit more involved one here. This particular circuit, you can again see the output of this circuit is not P and Q, or not Q and R, or not P and R, which can be reduced to this bottom one of simply not P and not Q and not R. And again, I have a simulator that we can look at that has the two circuits merged to prove that no matter what you do to either circuit, you will get the exact same output. So here we have the same two circuits here, but they're just merged together, getting from the same inputs here. And if again you watch the ones on the right hand side here, no matter what I do with the P's, the Q's, and the R's, you will see that the circles will have the exact same output as each other because they are identical circuits. So again, no matter what I do here, you'll see that everything on the right with those two circled numbers over there will either be a 1 or a 0, and they'll be the same as each other every single time. So the question is, how did we do that? Well, as we talked about the other day, we have this little table here with our logical equivalences, right? We applied, and I'd have to go back and remember what I did to reduce the circuit, which rules I applied, but we applied some of these rules here. Maybe some De Morgan, maybe some distributive, maybe some associative, maybe some commutative or commutative, some double negatives, who knows what, I don't remember, it was a while ago when I did this, but we used these laws, and that allowed us to go from the top circuit to the bottom circuit. So we have a much more efficient circuit. But we need to sort of take a step back here and see how this is really done in the world of computer circuits. We don't use P and Q. We don't use these same exact symbols. We use a little bit different symbols, but it's still all the same idea. but it's slightly different, and there's a few extra little things that we need to think about when we're designing a circuit. So we're going to learn more about the equivalent version of these kind of rules here that we use when we get into Boolean algebra, which is sort of part of the subject of today. So let's just take a look here at this weird little thought experiment for a moment. What I want you to do here is see if you can come up with a compound proposition that would be valid to make the outcomes be true, 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 false. Now, there's a really simple one that you can come up with, and if you see the simple one, that's totally fine. We can use that. We're also going to use a more complicated one or complex one to demonstrate a point. So I'm going to pause the video for a minute. Well, I'm not going to pause. You're going to pause the video for a minute, and I want you to take a stab at coming up with a compound proposition that can go right there where the question marks are, that would give us those values of true, 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 false, based on whatever P and Q's values are in each of those rows. All right, and we're back. So take a look here. This is the one that we're going to use here. Now, it's not the simplest one, and this can be reduced drastically. And some of you may have seen a simple one, which is just P or Q, right? P or Q will give us true, 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 false, okay? So why would I do this long, complicated thing here? Well, the reason is because this is going to help us demonstrate a point in a moment when we get into the Boolean version of this, the George Boole stuff. But here, let me make sure we understand the idea here. So here's what I've done. I've taken each set of P and Q combinations that give me a true, and then I've ORed them all together. So this set of P and Q is right here. That's true and true. This set of the P and Q combinations, when I have a P that's true, and then I have a Q that is not true, so true and false, I end up with getting a true. And then the last one, of course, same thing. If I have a P that's false, and I have a Q that is true, so not P and Q, that will also give me a true. So it becomes a true statement that if one of these things is true, I will get a T right here, okay? Now, at first glance, it might take a moment for that intuition to kind of sink in. So let's look at it in a deeper truth table here, okay? Here is the exact same truth table, but I've expanded it out. And we've done these kind of truth tables before. So whenever you have a truth table, you just take your 2 or 3 or 10 or however many variables, and you put together all of the possible combinations that you can have, which is exactly what's going on right here, right? That's every variation of P and Q you can have. And then we can quickly fill in the not P and the not Q, because it's just going to be the opposite of P and the opposite of Q. Next up, we're going to look and see what P and Q is, which is here, and that's also going to be here, as you'll see in a moment. And you'll see each of these individually are here and here and here. But let's just take baby steps. What is P and Q? Well, the first row, P and Q is true, because we have 2 trues here, right? And then the next one is false, 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 because we have no other case of 2 trues. All right? Next up, P and not Q, and we've done these truth tables a bunch of times now, so we're not going to spend a ton walking through each step here. But if we look at the next group, those are the values for that. And then the last group here, those are the values. Now, if I were to have, rather than doing that thing we did a moment ago where I just said, see if you can come up with this, random proposition or whatever, if I were to just have given you the assignment to come up with the truth values of that, well, what would you have done? You would have done exactly what we're doing right now. You would have got P and then not P and not Q and all this stuff, and you would have done all of these, and then you would have discovered that on the first row, this compound proposition, which is saying this or this or this, would be true, because look at that, one of them is true, right? And then we'd be saying the next proposition here, or the next row I should say, would also be true, because one of them are true, one of them is true, and one of those is true. Okay, so with all of that in mind, we end up with this result here, which is the result that we had on the original slide, like this. Okay, but this is a good breakdown of how we got there. And now you may be like, why are we doing this, Jeff? We've done this before. Well, we kind of did it backwards though this time. I showed you this, and you had to come up with all this, right? Why would we do that? Well, when we get into circuit design in just a minute, you'll see exactly why this makes some sense and why this is useful. Okay, but so the idea here is this. It's simply this. We look here and we say, hey, what gave us a true? What combination gave us that specific true? Oh, that's P and Q. Okay, and what gave us that, which is that? What gave us this specific true? Oh, that was P and not Q. And what gave us this specific true? Oh, that was not P and Q. Or all those together and you have this big compound proposition. Okay, so I want to make sure that part makes some sense. We're going to convert that into the ways of Boolean algebra in just a minute, but this idea needs to make some sense, okay? So hopefully that's good, and let's take a peek at the next piece of this that'll help pull it all together. So here's this guy, George Boole, right? And he, back in the 1850s-ish, somewhere in that range, was studying propositional calculus, this stuff that Aristotle came up with. And George Boole had this idea of compound propositions, right? And then about 100 years later, Claude Shannon comes along, and he is discovering George Boole's work, and he converts it into this idea to apply it to logic circuits, right? Which is where we're headed here. So between George Boole and Claude Shannon, this is how we get this new way of looking at Aristotle's 2,300-year-old stuff in a new light in the computer age, right? And so George's big contribution was this idea of compound propositions, right? Which is where we get all this ands and ors and nots and all this stuff. Claude Shannon's contribution to it was a way to do this mathematical circuit creation, right? Turning these equations into equations that are output of these logic circuits. So between the two of them, the notation is being changed here a little bit. So change number one, rather than P's and Q's, we switch to X's and Y's, okay? That's change number one. Change number two, and it's XYZ or WXYZ, right? Ultimately, the letters are irrelevant, but this is just the choice that they used. Next up, we get rid of this little weird negation symbol, and we switch to what we refer to as the Y bar or X bar or Z bar or whatever. We just use bar. In a minute, I'm going to show you a different notation than I use in the PowerPoint slides because it's just easier to type, but it's also valid. So we switch to this idea where we have a bar over it. This is like the complement and set theory. It's very similar to it's conceptually it's the same idea. Next up, we get rid of the and symbols and we treat this like multiplication. So you end up with this. So X right next to Y is just like X and Y, okay? And then X next to Y bar is just X and Y bar. It's no different than the previous slide here. It's the same thing, we're just removing it, and we do treat this like multiplication, except it's Boolean multiplication, which we'll see how that works out in a minute. Then the next thing is we replace the ors with plus symbols, and we get rid of the parentheses, and here we go, here's our new notation. And the last thing that we change is instead of trues and falses, we have ones and zeros. Okay, so that's the way it's done now, and this is the way we're going to use it moving forward while we're talking about circuits and circuit logic. But this is just the product of X and Y plus the product of X and Y bar plus the product of X bar and Y. So conceptually, this is not different at all from the propositional logic, right? Rather than saying true and true, if X and Y were both true, true and true gives us true, well, 1 and 1 gives us 1, and 1 and 0 gives us 0. 0 and 0 give us 0, right? The only thing that can give us 1 is 1 and 1. And then for a plus operation or an or operation, it's the same idea. 1 or 1 equals 1, or 1 plus 1 equals 1, right? 1 plus 0 equals 1, and 0 plus 0 equals 0, right? So that's the Boolean algebra way of calculating. So, but this is the notation. Now, the one I'm going to use in most of the slides, however, is this with the little tick mark above instead of a line above it, because it's just really hard to draw that symbol above it in PowerPoint. There is a way to create formulas, but it's kind of a pain, and especially as many times as we're using these formulas in here, it's just too much of a pain to do it. The other thing you'll hear is rather than Y bar, you'll hear Y naught or X naught or Z naught. And the one I use, which it is relatively accepted, is prime. And the only reason I do that is it comes from the back of my brain being a Rubik's Cuber. They use the tick marks for their algorithms. But this is the notation we're going to use. So Let's do something useful with it. Here we go. When we create a truth table with X's and Y's and ones and zeros, ultimately our goal is to make a circuit. We're not just doing this because we're bored, right? We're trying to make a circuit here, right? And these circuits are actually a function. And the function is defined of f of whatever your variables are. In our case, it's just x and y. If we had a third variable, x, y, z, it'd be f of x, y, and z. So the question then becomes, we need to create a function. What function can we create such that when I pass it in a parameter to here and to here, and that parameter is only going to be a 1 or 0, that's the only choice we've got, what would the function be such that I would get these results when they're passed in, right? So if I pass in a 1, 1, I'm going to get a 1. If I pass in a 1, 0, I'm going to get a 0. If I pass in a 0, 1, I'm going to get a 0. If I pass in a 0, 0, I get a 1. What would that function be? Well, that little weird trick I showed you a minute ago, where we just create a proposition, or in this case, an equation, using all of the ones that had a true, or in this case, a 1, that will actually give us this formula right here. And you'll see this is actually correct. So this is xy, which is if x and y are both true, which they are in the first row, we'll get a 1. And then this is x bar y bar, which is x bar y bar, will also give us a 1. So if that is true or that is true, here's our or, then we will get a 1. And if neither of those are true, then we get a 0. That's it. Now we just have to turn that into a circuit, which we're going to look at how to do that eventually here in a little bit. But this is the basic idea here. So let's put it to use. Everybody probably has this in your house, or you've been in somebody's house who does. It's one of these deals where you have two light switches that control the same light bulb, right? So we want to make a logic circuit that can accomplish this, okay? And we're going to do that by starting by creating our function. And we only have two switches, so we can let x and y represent the switches. And we can choose what the 1 and the 0 mean, is the on and off position or whatever. And let's just start with a function here. And we're going to say, just randomly off the top of our head, we can just randomly choose this, that if x switches in this position and y switches in this position, which we're going to call the on position, then we're going to say the light bulb will turn on. Okay, the function takes in the state of switch X and switch Y, and it comes with an output. It gives us an output of 1, okay, which means the light bulb is on. Now, we know now the next step is simply this. If I have 1 and 1 equaling 1, well, if I change Y, or if I change X for that matter, if I change one of the switches, that means the light's going to go off, right? So if I go to the next row, that's going to be a light off. And then third row, this is the tricky part, the light is also off in this situation, because we, again, think of the idea where both of them in this state means you're on. Well, if I toggle one of them off, I've gone from this state to this state. So I went from the on state to the off state, okay? And then the same thing holds true at the bottom here. If I'm getting to double zeros, well, I must have come from either this state or this state. Those are both off states, so this final state would be the 1 state, which is a true or on state. Okay, well that's it, that's our switch. And that is the actual slide we looked at just a minute ago, where we came up with the formula of xy plus not x, not y, right? So that being the formula, we can build this circuit right here. It's xy plus x bar y bar. Now I actually have in the circuit simulator this very circuit, so we can take a look at it and make sure that it actually does work the way we're expecting it to work. So here's the circuit. I know it looks a little different than it did on the slide a minute ago, but this is the same circuit conceptually. It's the same order of everything. And the whole idea is that basically if you look at the circuit here, whenever the switches are in the same position, right? If they're both in the on position, or they're both in the off position, or maybe we'll call it the up and the down position or something like that. But if they're both in the same state, then the light's on, otherwise it's off. So with that in mind, you see right now they're both off, 0 and 0, and the light's on, 1. If I switch either one, the light goes off, or if I put that back on, I switch this one, the light goes off. If I turn them both off, then the light's on. If I make them both on, then the light is on. So this is functioning the way we expected it to. So that's it. That's the basic idea, right? We went from this circuit right here by starting with the truth table where we sort of mapped out what we're expecting our circuit to do. Then we created our function, and then we took the function, we took its output, and we made the circuit. Okay. Now, again, we're going to be talking about reducing circuits. That's kind of the main purpose for today. But this particular circuit, it's already as far reduced as it can be. We're going to eventually get to some circuits that will need reducing, but let's just make sure we understand how to build the circuit from the beginning first. So let's look at a more advanced version of this, and that's the 3-switch circuit. Okay, it's the same idea, but we're going to again start off with this, just our variables and all the different positions, right? X, Y, Z. This is no different than what you do in a truth table for propositional logic, right? You have 2 to the third number of variables, 2 to the n, where n is the number of variables. You have 2 to the n number of rows in your table, right? So we have 8 rows here. And the first row, we're going to call that the on position, right? All 3 switches are in the same position, whether that's up or down or whatever. They're all in the same position. So we're going to call that on. So that's the first one. That's the switches on. Now, if you look at any of these cases here where it's only 1, 0, each of these here, those 3 that I've marked, that's 1, 0. What does that mean? We went from 3 1s down to 2 1s, which means we've only swapped or flipped one switch, which is going to turn it to the off position. So that's going to be off, that's going to be off. Now the next one here, this one, well, it's got 2 zeros, which means it was in a place of 2 1s. Well, 2 1s is an off position. So if we flipped another switch, we've now turned it back on, right? So now we're on, and then this red mark here, we said a minute ago, is going to be off. So that's off. And then down here again with the position of only 1, 1, that's an on position. The next one's an on position. And then the third one, why is it off? Remember in the 2 switch, if we had all 1s and all 0s, it was the same thing. This is different here. The reason it's different is because we just came from a state of having only 1, 1, right? If we had 1, 1, and suddenly we went from 1, 1 to no 1s, that means we went from whatever the state of having 1, 1 is, which is on, to having the opposite of that state, right? So we went from 0, 0, 1, or 0, 1, 0, or 1, 0, 0, pick, take your pick. Any of these 3 scenarios we know are on positions. So we went from one of those to suddenly flipping one of those switches, which gave us all zeros, or flipping that one, or flipping that one. That put us in all 0 position, which is why that is the off position. So that is our circuit, or excuse me, that's our truth table, okay? So what's our function? Well, it's again, every combination product that gives us a 1. So it's going to be x, y, z, or x, y bar, z bar, which is coming from here, or x bar, y, z bar, or x bar, y bar, z, right? And that is that function right there. So this is what the function looks like. And again, that happens to be fully reduced. I've already tried to reduce it and it can't go anymore. So let's look at that circuit. And there it is, okay? I've also got a simulator version of that, so let's take a peek at that real quick. Okay, here is the 3-switch light bulb, and remember this little thing over here, the green circle there with the number 0 in it, that is the light bulb, and then up here are our 3 switches. So at the moment, it's in the off position, 0, 0, 0. If I flip any one switch, it makes sense that the light just came on, right? So let's turn it back to all zeros, and I flip another switch, the light came on. The idea is no matter what state it's in, if I change one switch, the light bulb becomes the opposite of what it currently is, right? I mean, think about that with just a regular one switch light, that only has one switch on it. If you flip the switch, the light bulb goes to the opposite condition it's in. The light's on, I flip the switch, it goes off. I flip it again, it goes on, right? Well, all 3 of these switches need to work the same way. So no matter what I do, the moment I click a switch, I turn on the light bulb, or I do the opposite, which in this case becomes on. If I flip any other switch, it should go off. And it does. And I flip any other switch, it Should come back on, and so on and so forth. And no matter what I do, just one click toggles it back and forth between on and off. So that's the 3-switch operation. Again, no need to reduce this particular circuit, but I want to make sure we have a basic foundation on how to build these circuits, right? So we go through this process of putting out all the parameters we're going to need, coming up with the outputs that we're wanting, figuring out what the function is that makes it, then we build the circuit. Now the step before building the circuit is reducing the circuit if it can be reduced, which we're going to get to in just a moment, right? So this idea that we've been talking about here, where we're adding up all of the ones and making a big long formula here, that concept is called the sum of products. And what the sum of products is, it's just what we've been doing. It's this idea of what can I come up with, what term, what they're actually called min terms. What min term can I come up with that gives me that? And all a min term is a product of all of the variables that exist, right? In this case, it's x, y, and z. Sometimes it's more, sometimes it's less. But a min term is all of the variables are being used, and they have to be in such a state such that we'll get a 1. And we add, or we OR, right? The plus symbol is the OR symbol. We add all of those products together. And so in this particular case, the thing that gets us the 1 for the first row is just x, y, z. In the case of this one, the thing that gets us that 1, again, using all 3 variables, x, y, z, but it's x, y bar, z, because y is 0 in that particular case. To get this one, it's x, y bar, z bar. This one is x bar, y, z bar. And this is x bar, y bar, z bar. Okay? So all of those put together, we add them all up, or we OR them all together, and we end up with this equation right here. That is the function f of x, y, z. It's this formula right here. Now, as it happens, this particular formula can be reduced, okay? But I want to make sure before we get to any of that, we understand this idea here of what exactly is going on. This thing is called the sum of the products, and the products are all of the min terms, right? What are the min terms? The min terms are every single case using all 3 variables, that the combination of those 3 variables, whether it's themselves or their complement, right? Like in this case, we're using y bar, but it's either the variable or the variable's complement, but all of the variables that are in the truth table, what combination does it take to get a 1? And I want every single one of those combinations, right? That'll give us every single one of the ones in our truth table. We OR them all together. Speaking from the perspective of Boolean Algebra, we add them all together. That's the basic idea. So this is how you build your circuit. You start off with a truth table, you find out what values you're expecting, then you write your function by making the sum of the products and come up with this. Then you reduce it, which is, we're going to learn all about that in a little bit here, and then you build the circuit. So that's it. So speaking of building the circuit, let's build this circuit right here. This is what it looks like. This is the circuit, and I have a circuit simulator so we can see what it does. Okay, so let's take a look at that real quick. Now, just to be clear, this particular circuit doesn't have any real use. I just made up some random ones here in the truth table, ones and zeros, just to give us this particular function that was created right here at the top. So that function is right here now at the top, and according to this function, those min terms, the min term x, y, z, or x, y bar, z, or x, y bar, z bar, and so forth, that if I put any one of those combinations in, I should get a 1 as my output. And you'll notice at the moment it's at x bar, y bar, z bar, which is the last min term right here, and sure enough, I've got a 1. So let's go to this next min term right here, x bar, y, z bar, which in other words, just turn on the y switch. Look at that, still a 1, okay? Look at the third min term right in the middle, x, y bar, z bar. So x, y bar, z bar, and look at that, we get a 1. Let's look at the second min term, x, y bar, z. So x, y bar, z, we still have a 1. And then the first one is x, y, z, and we still have a 1. Okay, so this is partially proving that our function here is accurate, right? This particular thing, any one of those combinations did give us a 1, but what about the zeros? Well, this first 0 here is x, y, z bar. This one is x bar, y, z, and this one is x bar, y bar, z, which I conveniently have right here written down for us to look at. So if I am to put any of those combinations in here, I should get a 0 as my output. So if I go x, y, z bar, look at that, got a 0. If I go x bar, y, z, so x bar, y, z, I get a 0 output. And if I do x bar, y bar, z, so x bar, y bar, z, I still get a 0. So this circuit proves this truth table function to be correct and accurate. Now remember, this function that we've written right here, this is like a compound proposition in propositional logic that would normally be sitting right here. Well, if you were to go ahead and expand out this truth table and plug in all of the ones and zeros into this, you would find that plugging in this set of numbers into this formula will give you a 0. And if you plug in these in there, it'll give you a 0, and so on down the line. Now, it just so happens that this particular circuit can be reduced, all right? So here is the reduced version of it. This is the circuit and the function right here. So this is the new function right there, and this is the new circuit. What happened there, I don't know, but there we go. That's the new circuit. Okay, now clearly this circuit is much smaller, fewer components, and the function's way smaller, as we can see. And some of these functions, some of these truth tables, they might be such that if you looked at them hard enough and long enough, you could come up with this formula instead of the big long nasty one on the previous slide. But the bigger the truth table, or the more variables, or the more complex this is going to be, the harder it is to see that kind of stuff. And so the best way to do it is just get in there, write out the sum of the products, right? Get all of the combinations that give you a 1, and then reduce this, right? And we're going to go into how we reduced it in just a minute, how we got to this new equation. But that's the idea, right? Find the sum of the products first, and then reduce it down here, okay? Now, let's take a look at this particular circuit in the circuit simulator. So this is the reduced circuit. Now you'll notice at the top there I have the unreduced circuit, and then I have the reduced circuit. And the reason that's there is because I want to prove to you that both of those are the same thing. Both of those formulas, because this circuit and this particular thing right here, because this and this are the same thing. They are exactly the same thing. Then what that means is if I plug in any of these values, I will still get a 1. And if I plug in any of these values, I will still get a 1. So let's start with the reduced version right here, just simply x and z. So I click x and z, and I get a 1. X bar, z bar, I get a 1. And then y bar, z bar, which we're currently at the moment, y bar, z bar, I get a 1, right? So there you go, that works. Now, what if I plug in any of these? Well, because this circuit here is the same thing as this formula, it's just a reduced version of it with less components. If I do x, y, z, I will get a 1 still, because it's the same circuit. If I do x, y bar, z, I still get a 1. If I get x, y bar, z bar, I still get a 1. X bar, y, z bar, so x bar, y, z bar, still get a 1. And last, I get a 1 with all three bars, right? X bar, y bar, z bar. And further, to continue proving it, these over here on the left are the 3 0 ones from the table, right? These guys right here, the 0 here, this 0 here, and let me erase that, try that again. This 0 here, and that 0, and that 0. Those three functions, or those three products here, are those. And so if I choose any of those, I should get a 0 on my output. So x, y, z bar gives me 0. X bar, y, z gives me a 0. And then x bar, y bar, z gives me 0, right? So this demonstrates clearly that the bigger circuit and this reduced one have the exact same functionality. They do exactly the same thing with the exact same x and y inputs and z inputs. You'll get the same output regardless. So that's this particular function here. So the question is, how the heck did we reduce it, right? How did we do that? Well, if you'll recall, we have the logical equivalences from the logical equivalences chapter, which covered how to deal with this stuff for propositional logic, P's and Q's, and the ands and the ors and conjunctions, disjunctions and negation and all that stuff, right? Well, that's for propositional logic. Here in Boolean Algebra, we have the Boolean identities, and they're very similar, okay? So, like for example, this first one here, the law of double complement. Well, that's basically the double negation law, right? It's the exact same idea. So we're not going to dive in depth in these. We're going to look at a couple of them here, and we'll talk about them for just a minute. But we're just going to kind of see them in action, and we're going to walk through a couple of these where we algebraically reduce the formula. But then we're going to get to this thing called Carnot maps, which is way easier than doing it algebraically, and it's kind of fun to do, right? But let's just look at a couple of these real quick. So for example, De Morgan's law, right? We already know that one. If you look at it, you probably already get it because you're familiar with this version of De Morgan's law, right? It's still exactly the same. It still applies. If I have a product of two things negated and I apply De Morgan's law, it's the same thing as adding the negation of those two things, right? That's De Morgan's law. Distributive laws, associative laws, is just like regular old algebra where you can distribute things in, FOIL things, factor things, all that fun stuff. Commutative laws, and that's, x and y, or x plus y is the same as x plus or y plus x, and so forth, right? So these all are pretty familiar if you remember what's happening over here, okay? The identity law, we're going to use that one in a minute, and this should make some sense. If I say x plus 0, I get x, right? That's x or 0. If you think of it that way, x or 0 gives you x. And it's the same as this identity law right here. Let's clear out some of these markings here. The identity law, they're the same conceptually, right? Domination laws, same thing, okay? The idempotent laws, there's counterparts on each side of this, and they should be pretty intuitive. So let's walk through a couple things here and see if we can make some sense of all this. Okay, we're going to keep that on the left there so we can make sure that we don't get lost. And let's just start off with a simple equation here, okay? xyz plus xy bar z. We're going to reduce it algebraically, okay? Well, if you look at that, the first thing I can do is using the distributive laws, I can basically factor out an x, right? Because the distributive laws go both ways, right? You can factor in, factor out. Okay, so let's factor out an x, or excuse me, factor out an xz even, right? So we factored out an xz from this and an xz from that, okay? So now what we're left with inside there is y plus y bar. Or again, think of it like propositional logic, y or not y. Well, y or not y, that will always be true, won't it? Right? It's either yes y or no y, right? It's one or the other. Well, in our world, a true is a 1, right? So y or not y is just 1. And that's known as the unit property right there, okay? So that just becomes a 1. So in other words, we end up with x times z times 1. Well, even in Boolean algebra, if you multiply by 1, you get whatever you started with, right? So this just ends up being xz times 1, which just reduces down to xz. That's it. Pretty straightforward. All we did was apply some factoring and then the unit property, and that's it. So we got this simple little equation here. But let's prove it. Let's make sure this is really true, right? I mean, yeah, I can say it's true by those laws, but what if those laws are wrong, right? So let's look at this in a truth table here. My claim is that that and that are the same thing. And just without even looking at the truth table in any depth here, all you got to do is look and see that, yeah, those numbers are identical, or those values are identical. But how did we get there? Well, we started off with our three variables like we always do, okay? And we know that our ultimate compound proposition is going to be that. So what do? Well, we get all the pieces we need. So we're going to need a y bar because it's part of this, okay? And we're going to need an x, y, z, so we got that. And then we're going to need an x, y bar z. Okay, if you want to walk through the truth table, make sure all the values are correct, you can do that. But you'll see when all is said and done that all this pans out and these values are identical. So that and that are logically equivalent, right? The old triple equal sign. So if they're logically identical and you made a circuit using either one of those, well, then you have the same circuit. And of course, this XZ circuit is way smaller. Not only is it fewer components, but it's fewer inputs in general, right? In the larger equation, you have an X input, a Y input, and a Z input, plus you have an inverter, right? And you end up having two AND gates that have three pieces of input going into them, plus the OR gate, of course. Now this is just one AND gate and one OR gate. No inverters, nothing, okay? So it's a lot smaller and a lot less complicated. Okay, I think we're ready now. We've got the basic foundation here where we understand this concept of I have an idea of something I want to make, like a 3 or 2 switch light bulb, and I need to make a truth table, and then I need to come up with a function that gives me the values I want by calculating the sum of products, and then I need to reduce the circuit down, then I need to build the circuit, or reduce the equation down and then build the circuit. So let's do one from the beginning, all the steps. We're going to make this voting circuit right here. So imagine we have a committee of 3 people that decide issues for an organization, and maybe we want to make a little box or something they can put on their desk where they can secretly hit yes or no. So each individual votes yes or no, and as long as 2 people say yes, it passes. So let's make a circuit that can handle all this. So let's start off simple here, okay? Let's try to derive a function. We don't even have to necessarily do a truth table for this, but we can do it this way. So let's just say that x, y, and z are going to represent person 1, 2, and 3, okay? So we'll start there, and we know that the rule is only 2 of them have to say yes. So if we get x being 1 and y being 1 and z being 0, that's valid. Or if x is 0 and y and z are 1, then that's valid, and so forth, right? So in other words, that's a valid scenario where we want the output to be true, or 1, right? We have 1 vote yes for x, 1 vote for y, and then a no from z, but that's okay because x and y said yes. Here's another value that's true, or a combination that's true. And here's another one, okay, and there's actually one more. It's this one, where all of them said yes. That's also allowed, right? So because we only have 3 people, there are 3 variables, so our min terms are all going to contain 3 variables, x, y, and z, and they're going to be some combination of their value or complement of their value. So with all of these possibilities here, now our function is simply ORing all those together, right? And that's our function. F of x, y, z will be this function right here, which is all those things ORed together. Any of those scenarios, as long as any one of these is true, the output of this function will be 1. And if none of those are true, then the output will be 0, and we have our answer, okay? So now that we have the formula, we have the equation here, well, the next step is let's reduce it, okay? Because it turns out this one can be reduced quite a bit. So we start off with the function up there. I've got the properties, the identities on the left. There's our function we just built on the previous page. And let's take a look at it. In fact, maybe I'm not going to pause the video or give you too much time here, but maybe in between each step you can quickly pause it before I start talking again and see if you can come up with a next step that would work. Okay, so the first one is going to be just simply rearranging it to make factoring easier, right? I know it's a silly step and it's not part of the identities, right? But it sometimes just makes it cleaner to see the formula if we rearrange it a little bit. Okay, now that we've rearranged it, let's see what we can do. Maybe some factoring, right? Factor out an xy. So the xy only came out of this piece of it here, right? I didn't do anything with this. That's just going to get carried down right here. But we did factor out an xy. And the reason I would factor out the xy, you kind of look for these patterns. If you see a couple of terms together and you see that you have a term and then the terms complement, right? Z and Z bar. And if the other variables can be factored out, well, then you're left with a situation where you're going to be using the unit property again. Now, admittedly, it takes practice to spot stuff like that, but that's a good place to start thinking, right? Now that you've heard me say it, right? Keep it in the back of your mind. Okay, so that's just eventually just going to go away, right? So let's take a look at the next piece here, right? Per the unit property, as I said, that Z plus Z bar went away. And now, again, these pieces are just being carried down at the moment. We'll do something with them in a moment. Okay, in fact, maybe this moment right now. And the next step is this. We just factored out an x, right? And again, notice I left this last term alone. We didn't do anything with it. I just factored out an x from this piece here. That gives us that. And you're going to see a pattern here as we do that, where we just sort of work with 2 of the min terms and baby step our way through it. And then once we've done what we can with that, we work with 2 more min terms and so forth, right? So now, look at that set of parentheses right there. Do you see anything interesting in there? There's a y and a y bar, and then z. Now, there's nothing you can factor out of there, but there's something else that you can do that can help us to isolate that little trick there, that little piece there, right? And that's this. We can use the distributive law, where I'm taking the I'm taking the y, and I'm distributing it into this little product right here, which is going to give me y or not y, and, right, imagine an and right there, y or z, right here, okay? That's using the distributive law. And again, if you're not clear how the law applied or whatever, pause the video and take a look at the law over here, the distributive law, and just walk through it and make sure it makes some sense. And if it helps, bring up the propositional logic rules and compare the distributive law in there and make sure you can just sort of wrap your head around it. But now that we've used the distributive law, we can get rid of another one of these using the unit property, right? So let's do that. Get rid of it using the unit property. And again, this little guy has just been coming for the ride the whole time, right? We haven't done anything, well, not that one. We haven't done anything with him yet. We'll get to him in just a minute. But now we have this, okay? And really the only thing I can see here to do, I think, is maybe just factor that x back in and then see what's left. So let's try that, okay? So we just factored that x in. Now we got xy plus xz, and then we have this, okay? Well, now what can we do? Well, we haven't done anything with this, right? So maybe we can pull that z out. So let's try that, okay? So we'll factor out a z from these guys right here, okay? So that gives us this. And look, if you look there, you'll see that same thing we had a minute ago, right? The same idea that we had up here, where we have x or not x and y, which up here it was y and z, but it was the same idea. So the way we did that was we factored, right, or distributed, I should say, okay? And then after we distributed, again, this inside of the parentheses, we get x or not x and x or y, right? That's our distributing there. And again, of course, we can remove this per the unit law, and we're down to this. And now at this point, there's really not much left. I think if we just factor that z back in, we're going to have our final formula. So this is the final formula here, but it was this, right? It's a pretty big deal. So we've reduced it quite drastically. So let's go back to the beginning real quick. We wanted to build this voting circuit, right? We could have made a truth table, which is kind of what we did on that slide where we showed each of the combinations of x, y, z. But we could have done that in the truth table. But once we did, that basically gave us our formula, right? That was the sum of the products that gave us our function. That's what the circle at the top of the page here. Then we went through and algebraically, this is actually Boolean algebra laws, and we algebraically reduced it to this circle at the bottom. Now that we have the circle at the bottom, that's our final formula. Well, let's build the circuit, right? And we've done this already in the past using propositional notation, but let's do it using circuit notation now, or Boolean notation. So we know that's going to be the output of our final circuit, right? The output will be whatever xy plus xz plus yz was. So we need an OR gate that takes in 3 inputs. And what are those inputs? Well, it's going to be xy, xz, and yz, right? And how do we know that? We may not have been able to figure that out intuitively without going through the sum of the products, right? Because we had to think in terms of 3 people, but somehow we've narrowed it down to only 2 variables at a time even mattering, right? So that's the beauty of doing this reduction that we've done. But now all we need is the AND gates that each of those things came from, right? X and Y came from an AND gate, X and Z came from an AND gate, and Y and Z came from an AND gate. The end. There's our circuit. So here's the circuit in the circuit simulator. These are the 3 inputs, X, Y, and Z, and then there's our formula there, our function value, or a function definition, I should say, XY or XZ or YZ. So in other words, any of those combinations should give me the output of a vote yes, right? So XY gives it to me, XZ gives it to me, and YZ gives it to me. So that it works, okay? And now notice here that even all 3 of them being clicked still works. Then that is a requirement that all 3 have to be able, if they all 3 vote on it, it still should work. Well, it still does because this is the same circuit as that bigger one would have been had we built it, right? It is conceptually the same thing. If at any point we have only 1 yes vote, right now we've got 2, so we're still good, but if I have, anytime I have 1 yes vote, no matter who the one is, I'm always going to have 0 for my output over there, right? So I only have 1, I have 0. So the circuit clearly works the way we wanted it to. Now we can build it. Okay, so hopefully we're seeing the big picture here. We come up with an idea that we think can be implemented in a logic circuit, right? Light switches, voting, traffic lights, whatever, you name it, okay? We come up with the idea, we throw it into a truth table, we figure out the outputs of the function. We don't even know the function's definition necessarily right off the bat, but we figure out what we want the outputs to be based on the criteria given to us by whoever wants us to build this thing. Then we create the function by coming up with the sum of the products. Then we reduce it. Now we've only been reducing algebraically. The next tool we're going to learn is what's called a Carnot Map, which helps us reduce it visually instead of algebraically. So let's take a peek at those.